Hello and welcome to this chapter, where we will break down the transformer components and study each one of them alone to learn its role and how it works. Then we combine them together to get the transformer architecture. Be ready for this exciting journey as we have a lot of details to discuss. So let's start. In this video, we will learn about the first component of the transformer architecture, the embedding layer, which converts each word in a vocabulary to a unique vector of fixed dimensionality. These vectors capture semantic relationships between words, where words with similar meanings have similar vector representations, making them useful for various NLP tasks. In this video, we will use the word-to-vec embedding method, which offers two training algorithms, skip-gram and continuous bag of words. We will focus on the skip-gram architecture and see how to use it to get the input embeddings needed by the transformer as an input. To do so, first, we use a tokenizer that will transform a sentence into tokens. Each tokenizer has its own method, but the results are similar. We will study the different types of tokenizers in the next chapter. In general, the tokenizer will provide an integer representation that will be used for the embedding process. Now the tokenized text must be embedded to represent the meaning of words. Many embedding methods can be applied to the tokenized input, such as word-to-vec or glove. So, let's understand how word-to-vec embeddings work. The skip-gram architecture of the word-to-vec embeddings focuses on a center word in a window of words and predicts context words. For example, if the word tea is in the sentence of Claude Monet painted the Grand Canal of Venice in 1908. If the word painted which represents the center word in a two-step window. A skip-gram model will analyze two words before and two words after the center word. Then the window will slide and repeat the process for the entire text. The structure of the skip-gram neural network used to predict the surrounding words consists of two layers of weights. As the hidden layer consists of n neurons, and n is the number of vector dimensions used to represent a word. Both the input and output layers contain m neurons, where m is the number of words in the model's vocabulary. The output layer activation function is a softmax that outputs the word embeddings of the tokenized input words. The softmax will squash the output results between 0 and 1. And the sum of all outputs will always add up to 1. For each of the k output nodes, the softmax output value can be calculated using the normalized exponential function. For example, if your output vector of a 3-neuron output layer is v equals 0.2, 0.9, and 0.5, then the squashed vector after the softmax activation would be 0.229, 0.461, and 0.309. The question now is how the network learns the vector representations, so that it generates an embedding vector that contains the meaning of the words. Let's explain this step. After applying a two-word sliding window to the sentence, we will get the dataset required for generating embeddings, in the form of each word and its corresponding context words. Each of the words is represented as one-hot vectors before they are presented to the network. The softmax activation of the output layer nodes calculates the probability of an output word being found as a surrounding word of the input words. The output vector of word probabilities can be converted into a one-hot vector, where the word with the highest probability will be converted to 1, and all remaining terms will be set to 0. This simplifies the loss calculation. After training of the neural network is completed, you will get each row in the weight matrix representing each word from the vocabulary of your corpus. Only the weights of the inputs to the hidden layer are used as the embeddings. In other words, the weight matrix is your word embeddings. After training, semantically similar words will have similar vectors, because they were trained to predict similar surrounding words, as we will see in the next example. Suppose we need to perform embedding for a text corpus that contains the following sentence. The black wolf stealthily stalked the brown deer through the dense forest. We will focus on two words, black and brown. The word embedding vectors of these two words should be similar as they refer to colors. So, we will train a word-to-vec model on this text. And then we will get the word embeddings for these two words. First, we will import the Natural Language Toolkit library and download the punct package that contains pre-trained models for tokenization. Then we import specific tokenization functions from the NLTK library. Sentence tokenize is used to tokenize the text into sentences, and word tokenizing is used to tokenize sentences into words, and import the necessary modules from the Gensum library for word-to-vec modeling. First, we will read the contents of a text file that contains our corpus and store it in the text data variable. Then, the text data is tokenized into sentences using the sentence tokenize function. And each sentence is further tokenized into words using the word tokenize function. Additionally, all words are converted to lowercase. The result is stored in the sentences list, where each element is a list of words in a sentence. Next, we initialize and train a word-to-vec model using the tokenized sentences, and passing the minimum count argument that specifies that words with a frequency count of 1 or more should be considered when building the vocabulary. Vector size to set the dimensionality of the word vectors to 512. Window which defines the maximum distance between the current and predicted word within a sentence context of 5 words. At last, the skip-gram argument which indicates that skip-gram architecture should be used. Define the words for which we want to get their vector embeddings. Then we check if the words exist in the vocabulary using the key to index attribute of the model's word vectors. If both words exist in the vocabulary, then we retrieve their word vectors from the word-to-vec model and reshape them into 1 by 512 array. Now we obtained a vector embedding with 512 dimensions. These vectors represent the meaning of words in their context. These vectors are the input embeddings and they will be the main inputs of the transformer neural networks. To verify the word embedding produced for these two words is similar, we can use cosine similarity to see if the word embeddings of the words black and brown are similar or not. As you can see, the cosine similarity between black and brown is 0.99. The skip-gram produced two vectors that are very close to each other. So, it detects that black and brown form a color subset of the dictionary of words. The next step now is to use transformers to learn from word embeddings information, how these words can be associated and attend to each other. However, a big chunk of information is missing here, because no additional vector or information indicates a word's position in a sequence. As we know that the same word may have a different meaning when its position changes. And that is why we need positional encoding that adds positional information to the input embedding. And this is what we will see in the next video. See you then. Thanks for watching. Hello and welcome. In this video, we will discuss one of the most important components in the transformer's architecture, the positional encoding. As we know from the last video, we pass the embeddings to the transformer with no idea of a word's position in a sequence. The meaning of the entire sentence can change if the words are reordered. The transformer model does not use recurrence or convolution in its architecture, as it processes input data in parallel and treats each data point as independent. So excluding positional information will lead to missing a big chunk of context information. So we have to include positional information in the training process. Also, we cannot create independent positional vectors, as it would have a high cost on the training speed of the transformer, and make attention sub-layers very complex to work with. In that case, it will increase the memory footprint, and training will likely take longer as the optimization process needs to adjust more parameters due to the extra dimensions. The idea is to add value to the word embeddings. That helps the encoder capture the order and structure of the sequence, instead of having additional vectors to describe the position of a token in a sequence. This value is called the positional encoding. which is a mathematical function used to generate fixed-size vectors that represent the positions of tokens in the input sequence. These positional encodings are added to the word embeddings or token embeddings before feeding them into the transformer model. The purpose of positional encoding is to provide the model with a way to distinguish the position of each token in the sequence, as the self-attention mechanism alone doesn't have built-in knowledge of token positions. In the original transformer paper, attention is all you need. They introduced a mathematical method for positional encoding using sine and cosine functions with different frequencies and offsets. These functions are periodic functions that produce oscillating values. So, we use them to generate unique values for each position in the sequence, which are then added to the word embeddings to get the positional embeddings. A deep dive into the mathematical explanation of these equations is out of the scope of this course, but we will discuss how they work and how to use them to get the positional encoding, which is added to the word embeddings and then fed to the transformer's internal layers. The formulas look complex, so let's expand it. Assuming the model uses 512 dimensions for positional encoding and word embedding, we represent each token as a vector of 512 dimensions from element 0 to element 511. A position is an integer from 0 to a predefined maximum number of tokens in a sentence -1. For example, if the max length is 8, then the positions will be from 0 to 7. For every pair of elements, we calculate the angle in radians. Since we have 512 dimensions, we have 256 pairs of sine and cosine values. So, the value of I goes from 0 to 255. Then we concatenate them to get the final positional encoding vector. For example, we can calculate the positional encoding vector for the first token in the sequence where position equals 0. We can do the same calculations for all tokens we have. Here is the positional encoding vector for the second token in the sequence where the position equals 1. After calculating positional encoding vectors for all positions, we will get an array of positional encoding vectors for the sequence length. This is the positional encoding that will be added to the word embeddings to get the transformer's inputs. We will implement all these steps in Python in the fourth video of Chapter 8, which will teach you how to build your own transformer architecture from scratch. Great! Up to now, we have the positional embedding of each word. That contains the initial word embeddings information and the positional encoding values. Now our input text is ready to be processed by the encoder. And that is what we will learn in the next video. Thanks for watching. See you then. Hello and welcome to this video, where we will explain the encoder part of the transformer architecture. In this video, we will cover the following topics. What is the encoder and what is its role in the transformer? What are the components of the encoder and how do they work? How does the encoder process an input sequence and produce an output sequence? Let's start with the first question. What is the encoder and what is its role in the transformer? The encoder is one of the two main components of the transformer along with the decoder. The encoder is responsible for mapping an input sequence of tokens, such as words or subwords, to a sequence of continuous representations, which are then fed into the decoder. The encoder can learn to extract features from the input sequence that capture its meaning and structure, and encode the relationships between different tokens in the sequence. The encoder is composed of multiple identical layers, each of which has two sub-layers, a multi-head self-attention layer and a feed-forward neural network layer. The number of layers can vary depending on the model configuration, but typically ranges from 6 to 12. The output embeddings of each encoder layer have the same size as the inputs. The main role of the encoder stack is to update the input embeddings, to produce representations that encode some contextual information in the sequence. For example, the word apple will be updated to be more company-like and less fruit-like. If the words keynote or phone are close to it, the first sub-layer of each encoder layer is a multi-head self-attention layer. This layer allows the encoder to learn the relationships between different tokens in the input sequence. Attention is a mechanism that allows neural networks to assign a different amount of weight or attention to each token embeddings in a sequence, where each token is mapped to a vector of some fixed dimension. Self-attention refers to the fact that these weights are computed for all hidden states in the same set. To understand how the multi-head self-attention layer works, we need to study the self-attention mechanism first. The main idea behind self-attention is that instead of using a fixed embedding for each token, we can use the whole sequence to compute a weighted average of each embedding. Given a sequence of token embeddings x1 to xn, self-attention produces a sequence of new embeddings x1' to xn', where each x'(i) is a linear combination of all the xj. The coefficients wji are called attention weights and are normalized so that the summation of wji equals 1. The question now is why we need to average the token embedding. The answer is to make embeddings have context awareness and become contextualized embeddings. Let's explain this with an example. Consider what comes to mind when you see the word flies. You might think of annoying insects. But if you were given more context, like time flies like an arrow, then you would realize that flies refers to the verb instead. Similarly, we can create a representation for flies that incorporates this context by combining all the token embeddings in different proportions. Perhaps by assigning a larger weight to the token embeddings for time and arrow. Embeddings that are generated in this way are called contextualized embeddings. And thus, depending on the context, two different representations for flies can be generated via self-attention. Let's now take a look at how we can calculate the attention weights using scaled dot product attention. There are 4 main steps required to implement this mechanism. The first step is to project each token embedding into 3 vectors called query, key, and value. Then we compute attention scores using the dot product of the query and key. The third step is to compute attention weights using masking, scaling, and softmax. Finally, update the token embeddings using the value vector. Let's discuss each step in more detail. For projecting each token embedding into 3 vectors called query, key, and value, the input embedding and position encoding layers produce a matrix of shape, number of samples, sequence length, embedding size, which is fed to the query, key, and value of the first encoder in the stack. To get the query, key, and value vectors, the self-attention layer applies 3 independent linear transformations to each embedding. These transformations project the embedding, and each projection carries its own set of learnable parameters, which allows the self-attention layer to focus on different semantic aspects of the sequence. The second step to gain the attention weights is computing the attention scores, which tells us how much the query and key vectors relate to each other using a similarity function. As the name suggests, the similarity function for scaled dot product attention is the dot product, computed efficiently using matrix multiplication of the embeddings. Queries and keys that are similar will have a large dot product, while those that don't share much in common will have a little overlap or no overlap at all. The outputs from this step are called the attention scores. And for a sequence with n input tokens, there is a corresponding n by n matrix of attention scores. A mask value is now added to the result. In the encoder self-attention, the mask is used to mask out the padding values so that they don't participate in the attention score. Different masks are applied in the decoder self-attention and in the decoder encoder attention, which we'll discuss in detail in the decoders video. Dot products can in general produce arbitrarily large numbers, which can destabilize the training process. To handle this, the attention scores are first multiplied by a scaling factor to normalize their variance, so that we don't get too many large numbers during training that can cause the softmax to saturate. Some implementations use the square root of query size to prevent the softmax function from becoming too peaked or too flat when the query size is large. Now, to get the attention weights, we normalize the attention score with a softmax to ensure all the column values sum to 1. The resulting n by n matrix now contains all the attention weights wji. Finally, we need to update the token embeddings using the value vector. Once the attention weights are computed, we multiply the attention weights w by the value vector x to obtain an updated representation for embedding, or the contextualized embeddings x-i. But we don't use a single self-attention layer. We usually compute multiple sets of queries, keys, and values for each token and concatenate the output vectors. This is why we called it the multi-head attention layer, which is an extension of the self-attention layer. This means that the multi-head attention layer can learn to attend to different aspects or features of the input sequence, such as different positions, meanings, or contexts. The multi-head attention layer can improve the expressiveness and representation power of the self-attention layer. The second sub-layer of each encoder is a feed-forward layer. This layer applies a nonlinear transformation to each token individually, using two linear layers with a ReLU activation function in between, also called a position-wise feed-forward layer, because it processes each embedding independently instead of processing the whole sequence of embeddings as a single vector. The feed-forward layer can learn to capture local features and dependencies within each token. Each sub-layer has a residual connection around it followed by a normalization layer. This means that the output of each sub-layer is added to its input and then normalized. This helps to prevent vanishing or exploding gradients and to stabilize the training process. Skip connection adds the original word back to the output of the attention layer, so that it cannot be forgotten or ignored by the attention filter. This improves the robustness and performance of transformers in various sequence completion tasks. Skip connections allow information to bypass intermediate layers and avoid getting stuck in local minima or saddle points. They also smooth out the loss function and make it easier for backpropagation to find a good solution. Each residual connection is followed by a normalization layer to adjust the values of the inputs or the outputs of each layer to have a consistent range or distribution. This helps to avoid problems such as gradient exploding or vanishing, and improves the convergence and performance of the network. In summary, the input sequence is passed through each encoder layer sequentially. At each layer, each token goes through two sub-layers. First, multi-head attention layer, which concatenates the output vectors of multiple attention heads. Each attention head produces an embedding vector through 4 steps. 1. Project each token embedding into 3 vectors called query, key, and value, by applying 3 independent linear transformations to each embedding. 2. Compute attention scores using the dot product of query and key. 3. Compute attention weights by masking the attention score, then scaling the result by the square root of query size, and finally applying the softmax to obtain the attention weights. 4. Update the token embeddings using the value vector. Then, it applies a feed-forward neural network to its output vector and produces another output vector. The output vector of each token at each layer is then passed to the next layer as input. The output sequence of the encoder is the output sequence of the last encoder layer. This sequence contains the final representations of each token that encodes both their meanings and their relationships with other tokens in the input sequence. The output sequence is then fed into the decoder, which will generate an output sequence of tokens in another language or domain. As you can see, the encoder can process an input sequence and produce an output sequence that captures its features and dependencies. The encoder is a key component of the transformer architecture that enables it to learn from large amounts of text data and perform various natural language tasks. That's all for this video. We hope you enjoyed it and learned something new. In the next video, we will explain the decoder part of the transformer architecture and how it interacts with the encoder. See you next video. Thanks for watching. Hello and welcome. In this video, we will focus on how the decoder works and what are its components. The original transformer uses an encoder-decoder architecture. which means that they have two main parts: an encoder and a decoder. The encoder takes an input sentence, such as a sentence in English, and extracts features from it. The features are a sequence of vectors that represent the meaning and structure of the input sentence, as we saw in the last video. The decoder takes the features from the encoder and uses them to produce an output sentence, such as a translation in French. The decoder also considers the output sequence that it has generated so far so that it can produce coherent and fluent sentences. The decoder consists of a stack of n identical blocks. Each block has three sublayers: masked head self-attention, encoder-decoder attention, and feed-forward neural network. Let's see what each sublayer does. The first sublayer is the masked multi-head self-attention layer. It is the same as in the encoder with some modifications. It allows the decoder to attend to different parts of the output sequence so far. For example, if the decoder is generating a sentence in French, it uses self-attention to look at the previous words in French and see how they relate to each other. This way, the decoder can generate grammatically correct and meaningful sentences. But what about masked terms in masked multi-head self-attention? Well, masking serves to prevent the decoder from peeking ahead at the rest of the target sentence when predicting the next word. Without masking, the decoder could cheat during training by simply copying the target translations. So, masking the inputs ensures the task is not trivial. The decoder processes words in the source sequence and uses them to predict the words in the destination sequence. During training, this is done via teacher forcing, where the complete target sequence is fed as decoder inputs. Therefore, while predicting a word at a certain position, the decoder has available to it the target words preceding that word as well as the target words following that word. This allows the decoder to cheat by using target words from future time steps. For instance, when predicting word 3, the decoder should refer only to the first 3 input words from the target but not the fourth word keyed. The decoder masks out input words that appear later in the sequence. By setting the upper values to -infinity, we guarantee that the attention weights are all 0 once we take the softmax over the scores because e to the power -infinity equals 0. Other than masking, the decoder self-attention works just like the encoder self-attention, and produce the embedding vector through the same 4 steps. 1. Project each token embedding into 3 vectors called query, key, and value. By applying 3 independent linear transformations to each embedding. 2. Compute attention scores using the dot product of query and key. 3. Compute attention weights by masking the attention score, then scaling the result by the square root of query size, and finally applying the softmax to obtain the attention weights. 4. Update the token embeddings using the value vector. The second sublayer is the encoder-decoder attention. It performs multi-head attention over the output key and value vectors of the encoder stack, with the intermediate representations of the decoder acting as the queries. This way the encoder-decoder attention layer learns how to relate tokens from 2 different sequences, such as 2 different languages, as it allows the decoder to attend to the encoder output and learn the alignment between the input and output sequences. For example, if the input sentence is in English and the output sentence is in French, the encoder-decoder attention sublayer can help the decoder find out which words in English correspond to which words in French. This way, the decoder can generate accurate and faithful translations. The last sub-layer of the decoder is the feed-forward neural network, which applies 2 linear transformations and a ReLU activation to each position in the decoder output. This sublayer adds some non-linearity to the model, and allows it to learn complex patterns and relationships between the input and output sequences. Each sublayer in the decoder block has a residual connection around it, which means that it adds its input to its output before passing it to the next sublayer. This helps to avoid vanishing or exploding gradients during training, and improves the model performance. Each sublayer is also followed by normalization layer, which normalizes its output across dimensions. This helps to stabilize the training process and reduce overfitting. The final output is obtained by passing the output of the last decoder block through a linear layer and a softmax layer. The linear layer maps each position in the decoder output to a vector with v dimensions, where v is the size of the vocabulary and the number of possible tokens. The softmax layer then converts each vector into a probability distribution over v tokens, indicating how likely each token is to be generated as the next word in the output sequence. Until now, we have learned how the decoder part of the transformer's architecture works. And what are its components? We have seen that the decoder consists of a stack of n identical blocks, where each block has 3 sublayers: self-attention, encoder-decoder attention, and feed-forward neural networks. We have also seen that each sublayer has a residual connection around it, and is followed by normalization layer. We have explained how each sublayer helps the decoder generate coherent output sentences that are aligned with the input sentences. Finally, we have seen that the final output of the decoder is obtained by passing the output of the last decoder block through a linear layer and a softmax layer. We will implement all of this layer from scratch with Python in Chapter 8. You can move to it now if you want. That's all for this video. Thanks for watching.